one together. We've observed that if we have a representation of the group G, then it has a corresponding character, which is a function from the group to the complex numbers. It's defined by taking the trace of the functions of the representation. It's actually a class function on the group. The value of the function on an element only depends on the conjugacy class of the element. The space of class functions, in fact the space of all functions on G, has an inner product, a Hermitian inner product, taking values in the complex numbers. Using these, we can now state the big theorem. If I have two irreducible representations of G, call them phi and psi, then I can compute their characters, and then I can take the inner product of their characters, so that's going to be a complex number, but there's a formula for it. It turns out that's going to be either 1 or 0. It'll be 1 if they're equivalent irreducible representations, and it will be 0 if they're inequivalent irreducible representations. Therefore, we can say that the set of irreducible characters, that is, characters of irreducible representations, that's just what people call them, that forms an orthonormal subset of the space of class functions. That's the big theorem. Let me note in this statement here, irreducibility is crucial. We'll see what happens for more general representations in a bit. I'm going to prove this soon. What I want to do right now is get some consequences of this result, and there are a lot of good consequences. First one, so we would like to count the number of distinct irreducible representations, and this corollary says it. There are at most S equivalence classes of irreducible G representations, where what is this number S? S is the number of conjugacy classes in the group G. So this puts an upper bound on the number of distinct, meaning non-equivalent, irreducible representations. In fact, it's a finite bound. We know there are finitely many. So to prove this, first let's notice the following. If I've got two irreducible representations, and if their characters are equal, the theorem implies that the representations had to be equivalent. To check that irreducible representations are equivalent, we just have to compute the inner product of their characters. Oh, but hey, they're equal, so I could replace one of them with the other of them. So I'm actually taking the inner product of a character with itself. But of course, anything is equivalent to itself, and it's irreducible, so the theorem says that that's equal to 1. Therefore, we get to conclude that they're equivalent. Okay, so the set of irreducible representations up to equivalence is in bijective correspondence with the set of characters of such representations, which is a subset of the set of class functions. That's exactly by this fact here I just proved. But we know from the theorem that this set is an orthonormal subset. And the size of any orthonormal subset is less than or equal to the dimension of the vector space, which in this case, as we saw, is equal to the number of conjugate classes in G. So there's our bound. Another consequence. Let's take a representation and suppose it is a direct sum of representations, sub-representations, let's say, phi upper 1 through phi upper r, where each of the phi upper k are themselves irreducible. Then, if lambda is some other irreducible G representation, then I can compute the inner product of the character of phi with the character of this lambda. That's a complex number. It's actually, in this case, also going to be an integer. It's going to be equal to the number of the indices k from 1 to 1 to r, such that lambda is equivalent to the kth summand. This inner product of these characters counts the number of summands which are equivalent to the irreducible lambda in this direct sum decomposition into irreducibles. The proof is just a calculation. We know that the character of the direct sum is the sum of the characters of the summands. So we insert that into the formula. Now, because it's an inner product, it's additive in both variables. So we're actually looking at the sum of the inner products of phi k with chi lambda. And we know that this number is either 1 or 0, depending on whether phi k is equivalent to lambda. So this is counting exactly that number. Consequence: any two direct sum decompositions of phi into irreducibles have the same number of irreducibles of each type. That is, of each equivalence type. This is a uniqueness statement. If I write phi as a direct sum of irreducibles in two different ways, the lists of irreducibles, those two lists, and those two direct sum decompositions have to be the same lists up to equivalence and reordering the lists. That's an immediate consequence of this proposition. I can compute the number of times lambda appears in the list of summands up to equivalence just by computing this number, which doesn't depend on the direct sum decomposition. This is just directly from phi itself. I don't need to know that it even has a direct sum decomposition to produce that number. So let's put all this together. I'm going to write lambda upper 1 through lambda upper r for a complete list of pairwise inequivalent irreducible representations of G. So every irreducible representation is equivalent to exactly one of those lambda i's. Now we can say the following. If phi is any G representation, then it is equivalent to something I'll write as m1 lambda 1 direct sum up through mr lambda r, where the number mk, that's an integer, it's exactly the pairing of chi phi with chi lambda upper k. That's a integer. In fact, it turns out to be a non-negative integer. And let me explain the notation here. When I write m, a number times lambda, that means a direct sum of that many copies of lambda. So if I have a representation and I want to know how it is a direct sum of irreducibles, which I know is essentially happens in one way, I just compute the inner products of the character with the character of irreducibles. I'll get integers, and that tells me how many sum-ins of each type there are. This is, again, just a calculation. So we know that phi is completely reducible because all finite dimensional representations are. So there exists an equivalence of that type. Phi is equivalent to, m1 lambda 1, direct sum up to mr lambda r, because I've accounted for all the irreducibles. I can assume they're lambda 1 through lambda r. I don't know what the mk's are yet. I just know that they're non-negative integers. But now I can compute those numbers using the character. If I compute the pairing of the character of phi with that of lambda k, well, this thing is a direct sum, and therefore its character is a sum. So I'll write it as the sum of I goes from 1 to r, mi chi lambda I, but I'm pairing that with chi lambda k. And of course I can pull that out of the sum because it's linear in the first variable, so I'll get mi times that inner product. But the theorem says that this term is either 1 or 0. I could write it as a Kronecker delta. It's 1 only if I equals k. So we learned that this was just mk. So this calculates the coefficient. By the way, in a statement like this, the numbers mk are called multiplicities of the given irreducible lambda k. Now we get a consequence which we have wanted. If I have two representations of the group G, then they're equivalent representations if and only if their characters are equal. In other words, the characters are a complete equivalence invariant of the representations. We actually knew this direction already. If the representations are equivalent, their characters were equal. But now we've got the other direction too. You see, if the characters are equal, then the character determines all the information we need to compute the coefficients in this formula. So if two representations have the same character, they're both going to be equivalent to the same direct sum of irreducibles. So they're equivalent. Okay, one more consequence. If I have a representation and I write it as a direct sum of this list of standard irreducibles, so again, the lambdas are a complete list of inequivalent irreducible representations, so the mk's are the multiplicities, then, well, I can compute the inner product of the character of phi with itself, and there's a formula for that. That just turns out to be the sum of the squares of the multiplicities. And this has a consequence. That inner product is equal to 1 if and only if phi is itself irreducible. In other words, we get a criterion for when a representation is irreducible just in terms of its character. Just compute the pairing with itself. If it's 1, it's irreducible. If not, it's not. So the formula is just a calculation again. So these are each a sum, from I goes from 1 to r, of the multiplicities times the character of lambda I. Do it again. We can pull this out of the sum because the inner product is biadditive, so we'll get a sum over both I and j, mi, mj. Notice, in general, I have to put a complex conjugate over something I pull out of the second variable, but mj is an integer, so I don't have to do that. It's already a real number. So we get that formula. But again, the theorem tells us that this is either 0 or 1. So that gives me the formula. Now you can ask, when can this be equal to 1? Well, that happens if and only if one of those things is 1 and the others are 0. That's the only way that can happen, because it's a sum of positive or non-negative integers. And of course, if this is the case, that's saying exactly that phi is equivalent to lambda k. So it's irreducible. So basically, the orthogonality relation, which is what this is called, is the whole ball game. And I'll prove that soon.